I won't touch it again. Good. So I'll very quickly go through an introduction to generalized Gibbs ensembles, just in case anyone didn't quite make it to the first talk today. So normally in statistical mechanics, we have states and we'll label them by n, and the state has some probability of occurring Pn. And to find these probabilities, I want to maximize the entropy of the system. And then usually, if I just have a standard system, I want to normalize my probabilities so they sum to 1. And I have some average energy constraints as well. So if I maximize the entropy subject to these two constraints, I get just a Gibbs distribution where it's the exponential of minus the energy divided by the temperature. So beta is 1 over temperature here. But if I'm in a system where I have additional conserved quantities, then I should also impose that I want to constrain the entropy and maximize it over these average values for the extra conserved quantities as well. And doing so leads now to a generalized Gibbs distribution, where in the exponential I have the energy and the eigenvalues of all of these other conserved quantities in the state n. And this normalization constant, this 1 over z, is then going to be the sum over all of these exponentials. And in an abusive terminology, I'll refer to this as my generalized Gibbs ensemble. So if I want to study a system where I have these additional conserved quantities, I'm going to focus on just the two-dimensional case for now. So I assume that my system lives on a strip, size of length r and l, and I'm going to be working in a quantum theory. So I choose some slice. This time I'm going to choose a vertical one that I want to quantize my theory on, and my Hamiltonian is going to be given as the sum over all of these charges, each with their own chemical potential. So these charges will depend on this length r, and then I evolve horizontally. So my partition function is just going to be the sum over, again, exponentials of the eigenvalues of each of these charges. Now, there was no reason a priori that I should have chosen to quantize on a vertical slice. So instead, I could have quantized on a horizontal slice. So now if I quantize on the horizontal slice, I have some different Hamiltonian that I'll denote h tilde, which will now depend on the length L, and it'll have eigenvalues e tilde. And so this time, the partition function is the sum over these e tilde energies that have been exponentiated. But it's exactly the same system, so there should be an equivalence between these two partition functions. And choosing these two different quantization slices is equivalent to doing an S transformation on the torus. So if this theory, if I treat it as a torus where I identify the top and the bottom and the left and the right, then my usual modular parameter that I have is I times R over L. So going between tau and minus 1 over tau, which is the S transformation, is exactly this relation here, quantizing on the two different slices. So the goal of what I want to study is if I go back and I start with this Hamiltonian built out of all of the conserved charges that I have, if I know all of these eigenvalues here, can I then calculate the E tildes? And there's various reasons you'd want to do that. Mathematically, it's an interesting problem because there's various modular properties already of the Gibbs ensemble that you understand. So you want to see if the full Gibbs ensemble has nice mathematical properties at all. Physically, you want to do this because understanding the modular transformation can then be used to calculate things like the density of states of the original generalized Gibbs ensemble, which relates through holography to black hole entropies. In the thermodynamic limit, I want to have this density of states as well. So there's both mathematical and physical interest in determining these E tildes. So throughout the rest of the talk, if I say generalized Gibbs ensemble, I'm talking about this one here, where I sum over these eigenvalues. And if I say the transformed or mirror GGE, or generalized Gibbs ensemble, I'm talking about these E tildes here. Now, I need to have a theory where I have all of these additional conserved quantities to build a generalized Gibbs ensemble to begin with. And we've already been introduced to 2D CFTs yesterday by Tomasz and Sylvain. So they were looking at cases where I was extending the Virasoro algebra that I have in a 2D CFT, so either into a WZNW model or into a WN model. But I'm going to just focus on the case where I only have the Virasoro algebra. So recall from yesterday that the Virasoro algebra is given by these modes Ln, and you can show that using just these ln's, I can build an infinite set of charges that all mutually commute with each other. So these conserved charges are going to be what I insert into my generalized Gibbs ensemble. So my Hamiltonian is going to be a sum over all these charges. And here, when I take a trace, I'm going to be tracing over different representations of the Virasoro algebra, and these representations are building up my full theory. Good. So now that we've introduced the charges that we're interested in, I just want to take a brief detour to talk about a physical interpretation for these generalized Gibbs ensembles that will help us have just a little bit of physical intuition of what we're going to find when we try and do this modular transformation. So in my GGE, I can, instead of thinking about my Hamiltonian as a sum over all of these additional conserved quantities, I can think of it as, if I go back to my rectangle, I've just inserted a defect that runs horizontally, where the defect operator is just a sum over the exponential of these additional conserved quantities. So as I evolve, I then hit the defect, and then I continue evolving horizontally. So now, when I do the modular transformation and I quantize on a horizontal slice, my quantization slice is now cut by this defect. So this shows us that we have a non-trivial transformation. If I didn't have the defect here, we would have modular invariance, and that's very powerful. It's been used a lot to constrain possible two-dimensional CFTs. But in this setup, I'm now expecting that these E tildes that I wanted to compute are going to be quite a non-trivial transformation from the original eigenvalues of these charges. So the goal can be reformulated as not just understanding these E tildes, but trying to understand what this theory is where I have some Hilbert space that's now being intersected by a defect. Now, in order to try and solve this problem, I'm going to use the thermodynamic beta ansatz. So the thermodynamic beta ansatz is a nonlinear integral equation where the driving term has these pseudo energies E that depend on a rapidity for the quasi-particles, theta. So I want to solve this nonlinear integral equation, which has a kernel that's related to the scattering matrix of the theory. So I assume that I can think of this 2D CFT as some set of quasi-particles with a 2-to-2 scattering. So it's integrable. And then once I solve this nonlinear integral equation, I then plug in my solution epsilon into this integral here, where P is then the momentums of these quasi-particles. And this will give me the energy of my theory. So if I just integrate here over the real line, this will give me the ground state energy. If I instead start to deform the contours, there are various singularities of the log. So I can reformulate that as an integral back over the reals with some additional pieces in the driving term related to the S matrix, and that will give me the excited states. So by solving these nonlinear integral equations for different contours, I can then get every energy from my theory. So in the original generalized Gibbs ensemble, sorry. So if I want to then look at quantizing on the other slice, I then have to do what's called a mirror transform of my GGE. So quantizing on the horizontal instead of the vertical slice is like swapping the space and time. And this can be, in terms of the GGE, formulated as swapping the energy and the momentum. And this then gives me the mirror TBA equations. So now if I want to find my energies of the transformed GG, so the E tildes, I then just have a different driving term. I solve a different nonlinear integral equation, and now I plug my solution into a different energy integral to get back these transformed energies. So in the case of the generalized Gibbs ensemble, I can know from the work of BLZ that if I want to find my original spectrum, so where I've got the eigenvalue of these higher charges, I solve this equation with just an e to the theta. And then in my energy integral, I have one exponential here, e to the theta, that gives me back the Hamiltonian. And this e to the 5 theta will give me back the I5 eigenvalues. So here I'm explicitly looking at the Li-Yang model. So I just have one nonlinear integral equation to solve. But this structure is true for any minimal model which can be realized as a set of potentially coupled TBA equations. So then if I use my mirror transform, I swap this piece now into the driving term, and the driving term here becomes the kernel in this integral. And so by solving this new TBA equation, I can find the E tildes that I want. And to go back to talk about the defect interpretation, we can find if you want to derive these TBA equations and you assume that not only do your particles have 2-to-2 scattering, but there's also a purely transmitting defect present as well, you'd get a transmission factor here in the driving term. So we can think of this e to the 5 theta piece as being the transmission factor of some defect. So now that we have the nonlinear integral equations that we want to solve, we can sit down and numerically try and solve them. So they're too complicated to get analytic expressions for the solutions. But if we first start again in the Li-Yang model, and we just look at the ground state energy. So there, I know what the ground state should be of my theory when this parameter kappa 1, which was related to the chemical potential, is 0. And then I find that as I increase kappa 1, I can numerically solve it, and I have a monotonically increasing function of my ground state energy. Now, this monotonically increasing behavior lends itself to an interpretation as an irrelevant RG flow. And this isn't too surprising, because if I go back to the defect, I have some current that I've integrated over, and this current was an irrelevant operator to begin with. So you could think that maybe introducing these extra charges can be thought of as inducing some sort of irrelevant RG flow on your original CFT. And so we want to see if this interpretation holds true for the excited states. So again, I've just picked one example that we've solved numerically. So if I take one of the excited states that's equivalent to a level 2 excited state in the Li-Yang model, then again, when kappa 1 is 0, I just get the Li-Yang value for the energy of this state. And then as I evolve and increase kappa 1, I then get my energy just starts to change, but it stays real. However, we then find at some critical value of kappa 1 that my energy splits into a complex conjugate pair of energies instead. So this phenomena has also been observed if you repeat this whole process for free fermions, where you can do it exactly. But this was a bit of a surprise to us that you have this kind of splitting into a complex conjugate pair. And what you would then expect is if this energy has split into a complex conjugate pair, there should be some other energy that it has collided with. And indeed, numerically, we can try and find this extra solution. So we solve our TBA equations and now find a solution where the energy diverges as kappa 1 goes to 0. So this state, as I'm going back towards my IR CFT, because I'm flowing from IR to UV this time, the energy becomes infinite. In my partition functions, I'm taking exponential of minus the energies. So this state seems to drop out. So it looks like we can observe some state coming in from the, as I go from IR to UV, I do indeed seem to get new degrees of freedom entering into my theory. So as I said at the beginning, this is work in progress. So we're still working on trying to sort out all the details of the solutions to these TBA equations, understanding if we have a solution, does it have to physically be included in the transformed GGE? So unfortunately, it's quite an abrupt stop to the talk there, but we're still working on other excited states. We find this phenomena of real energy splitting into a complex conjugate pair again. So I'd just like to end with some future directions. Some of them are more immediate. So we want to fully understand the modular transformed GGE spectrum. Can we understand why we have this critical value where the energies become complex? We then want to understand if the states are arranged in some sort of multiplet structure. I had these two states coming in and colliding together to split into a complex conjugate pair. Is there some sort of symmetry present that relates these states with each other? By studying analytically the highly excited states, it seems there is some sort of multiplet structure, but we haven't worked it out fully yet. I've said a few times this idea about going from the IR and flowing up to the UV. Does this even make sense? Maybe it's just absolute nonsense to even try and think of it in this kind of physical term. Maybe if I just want to include a finite number of charges, it doesn't make sense, but I have an infinite number of charges I could include in these GGEs. And if I include all of them and finely tune all of their coupling constants, maybe I can then flow to a more sensible looking UV theory where I don't get these complex energies. So this is analogous to some work that's been done by Leclerc and others in the case of TT bar deformations, where they flow from the IR back up to the UV. I can then also try and think about this defect that I introduced. At the moment, we just see it as a useful picture, and we have this transmission factor looking term in the TBA equations. Can I have a more concrete physical description of what this defect is? So one possible way to do this is to go back to the lattice and try and redo these GG calculations on a lattice and then take continuum limits and see if there's some sort of concrete physical picture for the defect there. As I mentioned at the start, I can then take these calculations and use them to compute corrections to various things like the density of states. And then through holography, I could go back and try and relate this to black holes that are related to higher spin gravity theories. And finally, something that we'd like to do is try and develop the OD-IM correspondence for these modular transformed theories. So in this modular transformed GGE, I can again, if I go back to the TBA equations, if I just had an e to the 5 theta here when alpha is 0, that gives me the higher charges. So if I just keep this modified driving term, but start to put an e to the 3 theta, 5 theta, so on, do these actually encode the eigenvalues of conserved quantities in this transformed theory? If it does, then can these higher conserved charges for the transformed GG be encoded in an ODIM correspondence like the ones that were discussed yesterday? So with that, I'll end there, and thank you for listening.
Thank you. Are there any questions?
So the result that you find and also the construction with the charges is reminiscent of TT bar. In particular, you can write TT bar flow equations for the higher charges as well, the higher spin charges, and you can essentially get differential equations that generalize the usual one. And I suppose you could try to solve them if you know the original spectrum. Have you checked if what you find from this direct TBA matches with these differential equations?
So we have a slightly different setup from the TT bar case where, from what I remember in TT bar, what you find is that you have here some extra CDD factors in your S matrix, and that's what gives the TT bar deformation. And so there I can pull it out, and if I still had some length scale here, I then get a length scale that depends on the energy, and that's how I get my equations. Whereas here, I just have a fixed, just a fixed constant here. So we don't seem to be able to get the same kind of flow equations or the same kind of...
So what you're saying is true for TT bar proper, I think. You can do generalized TT bar using GG. So this is a paper by Stefano Negro, Guzman, Hernandez, Chifre, and myself, where we write these equations. And you have the same picture where you can rotate and you get a defect. And I'm not quite sure right now whether you will get the very same equation, but I think they will look pretty similar. So
yeah, okay. I think if I'm thinking of the paper you're talking about, what we're doing, I think, would be equivalent to the initial conditions of your differential equations.
Mm-hmm.
So I think what we want to try and find here can't be found by solving your differential equations. We would want to input it as an initial condition for your kind of differential equations.
Not even as you vary the parameters.
Yes, no, not, yeah, this parameter is not the same kind of flow generating parameter. Yeah.
Okay, thanks.
Thanks for the talk. Do you have any control over where these points start to appear, where you get new states out of nowhere? For example, if you look at the density of states, maybe some analytic properties of that would predict where these things occur.
Sorry, can you say that again? Where which things occur?
Where you have the splitting of new states, where you get exactly this picture here.
So in this case for the Li-Yang model, we just have to solve it numerically. And what we find that I haven't made clear here is that this point depends on the state. So a level 4 state will actually split sooner than the level 2 ones. So at this stage, in this more general case, we don't have good control over it. What we can do, though, is do it exactly for the free fermion model. When we do it there, what you find is there's a way to write these energies as sums over all of the other KdV charges. And there, this sum is asymptotic. Oh, sorry, this sum is not asymptotic for the excitations above the ground state, but it has a finite radius of convergence. And that radius of convergence is exactly then related to where we get this splitting into the complex energies. So in that case, we have complete control and we know roughly why the splitting occurs and where. But in these cases, we don't have any analytic control over it at this stage.
All right, thanks.
One final question.
Thank you. I have a question about the setup. So essentially, you're proposing a modular transformation between GG and GE.
Yes.
So do we know that there's kind of enough space, this resulting GE to, and if I consider standard modular transformation, it's between GE and GE. So somehow by analogy, I would expect that if there is something like this, it would also require GG on the both sides.
So what we find is I didn't talk about it, but what you can do is start with the generalized Gibbs ensemble. If you want to expand it as a power series in alpha, you can then transform each term, and we know how to resum it. And what we find there is that that result does give you what looks like another GGE, but that can only be an asymptotic matching to begin with. And we find if I wanted to originally restrict my GGE to just have the KdV charges, when I do this transformation and resum, generically, I actually end up with the KdV charges and other conserved quantities that don't commute with them on the other side. And this, we can do it to all orders, and we see these charges, but we have no real good conceptual idea of why these additional charges are now entering the picture as well.
Okay, so let's thank Max again.
So again,